Okay, so it's recording. Welcome to part 2 of lecture 7. And we closed the part 1 of this lecture by discussing the very weird fact that if you decide to throw electrons against the double-slit experiment, you are going to see that actually the electrons seem to provide an interference pattern as they would be waves. Okay, so I I I would like to show you a video with. I mean, it's a very old video. I watched that when I was not even at university, and so that's why I'm going to show it to you because I know the video. And but of course there are several different nice tools in the internet that you can use, and I can also try to point out you to them. So I will share my screen. Um, so do you see my screen? So it should be a page. So do you see this Dr. Quantum double-slit thing? I have to go back to the. Okay, so let's watch the video, at least one part of it, because the other part I don't want to tell you. Okay, okay, so just a second. Okay, I will play and let's see.
Hello.
Hi.
Please, we can't hear.
Sorry.
We can't hear.
Ah, you can hear the audio of the video.
Yes.
Okay, so let me do the following. I will send you the link of the video and we watch together, okay? But actually, it's not important to hear, okay? Yeah, you don't have to listen. Let me go to what matters. So here he has a cannonball, and he will start shooting the cannonball, but just with one slit. And you see that he's going to see a pattern. So let me just go back. You see that the cannonballs, they are concentrated in this region. Of course, I mean, some of them, as I said, will hit the corner of the slits and can bounce to other corners, but they will be concentrated just in front of the slit. Okay? So he's going to add the second slit now. So you have the double slit experiment, and he'll start shooting with the cannon. And this is what you're going to see. So if you see the pattern, you're going to see a concentration of particles again in the region that is in front of the slits. Okay. And he's moving now to the waves. Okay, so he's going to send waves of water, and he'll do the experiment with one slit and then move to two slits. So you see that the wave is going through the slit, then there is diffraction, and then it acts as a primary source, and you see that the waves are now hitting the screen, and the highest intensity of the wave will be the one just in front of the slit. But you also see that if you move away, you're going to see the intensity getting lower. But So it's not a concentrated amount of I mean, the wave is not just hitting this singular part, but also it distributes. It's a delocalized thing that distributes over. Now he's going to change the setup from one slit to two slits. So you see that the wave, when passed through the slits, there is diffraction. So this wave now this slit will act as a primary source. This slit will act as a primary source, and you have new waves being produced here that will interfere. So there is a superposition. So there is interference, which can be destructive or constructive. Okay. And you see now that the pattern is completely different from the pattern with particles, because now you have spots on the second screen where you have a bright well, line, or at least, you know, this space here, but also you have dark spots. So this is where the waves interact destructively. So just to remind you, this is with particles and this is with waves. So waves interfere and particles do not. That's the essential bit of this experiment. Now he's saying that he's going quantum, so he's going to perform the experiments with electrons. So he says that, well, he's going to throw electrons, and electrons are really tiny, tiny bits of matter. And he's going to, so this is the gun of electrons that he has, and he's going to shoot electrons against one slit. And you see that this is very similar to what we have seen for the particle situation, right? There is a concentration of particles just in front of the slit. Now let's move to two slits. So he gets completely surprised that after waiting some time, he sees an interference pattern as he saw for waves. Now he's going to say the following: this does not make sense. So let me do the following. I will simply reduce the rate of shooting of electrons, because it might be that electrons, when they cross the slits, they interact with each other and they are deviating each other from the trajectory, original trajectory. So if I send one electron per unit of time, then I will be sure that I'm shooting just one electron, and they will not interact with each other, okay? So you're going to see the pattern that will be constructed, but he's going to wait long enough, as we discussed. So he's going to shoot the electrons and wait a long time to see what's going to happen. So he says, after 1 hour, the wave interference pattern just returns. Okay? So this thing that he's explaining now is that the electron, the only explanation that he sees is that the electron comes towards the screen. Arriving at the screen, it passes through both slits and interact with each other. But this is a rather I mean, this is not so. There's not a well-defined and consistent physical description. Okay, now he's just explaining in an easy language in order to make this explanation. But what he's really saying is that, well, the only explanation that I see is that electrons have to behave as waves in order to produce an interference pattern. Okay. Before I show the rest of the video, I want to continue with the lecture. So let me go back. I will stop sharing and come back to my boring slides. So do you see my slides now? Okay, so let me see the chat. Yeah, so the link of the video was posted. Thank you for that. Yeah, sorry that you could not hear, but I tried to, explain the details. And then there is a question: if particles do not interfere, how did we come about the normal curve? Can you explain a bit better what do you mean by the normal curve? So, yeah, while Grace elaborates on that, I just want to say that I hope that, so the purpose of this video was not to give you a physical explanation of what's going on, but rather to give you a visual explanation of what is going on, okay? When we were discussing the cannonballs, so the cannonballs, what we saw is that when they pass through the slit, and you have the two slits open, there is a chance, a very higher chance of finding the cannonballs in the region in front of the slits. Okay. So the region that goes from one slit to the other is the region where you are going to find most likely the cannonballs. But particles do not interfere. Okay, we found out that probability of both slits open was the sum of each probability. No, this is so. Okay, that's an important question. So you're saying that because you're summing the probabilities, this could be like some sort of interference. Be careful with that, because interference is the phenomenon that we have discussed in the wave situation. So when we discuss the wave behavior, and there it was important to sum the wave functions and then compute the intensity of the sum of the wave functions. And the intensity is the thing that you measure. Okay, so first you sum the wave functions, and then you take the square. If we summed the intensities, this would be the analog of summing probabilities. Okay, so what we do there is different. Before we sum the wave functions, and then we compute the intensity. Here we are if you take the analogy, we are directly summing the intensities. So in the language of probabilities, this means that we are adding the probabilities because the events are independent of each other. So it is precisely because they don't interfere that you sum probabilities, okay? In the case of waves, you sum the wave functions and not the intensities. This is absolutely crucial to understand that, okay? But your question is very important, okay? Good. Okay, so now that we are seeing this very weird thing about electrons arriving at the screen in an interference pattern, we have to think, well, if there is an interference pattern, namely some regions where there is a constructive interference and some regions where there is a destructive interference, then I have to describe the electron. If I want to describe with things that I know, I have to describe the electrons in terms of a wave, because if I describe electrons as particles, I will go back to the probability distribution sum, and this is not giving the result that I see on the experiment. So I have to describe the electron with some sort of wave, and this was exactly what de Broglie proposed, that there is a wave associated with each particle. So these properties A and B that we discussed, they suggest that electrons they behave as classical particles. But C and D suggest that the electrons behave as a wave. So I have to find somehow a description that will mix these two things, okay? So the electrons, as any other particle of matter, they are neither, this is very important, they are neither particles nor waves, okay? They behave, as we just listed here, in a very weird fashion, such that they have some particle properties, but they also have some wave properties. What are they? That's a very good question. Well, we don't know. We don't know in the sense that we don't have a word for that. Okay, you can call it whatever you want. It's not what we call as particle. It's not what we call as wave. It is a particle wave dual. It sometimes behaves as a particle. It sometimes behaves as a wave. The important thing is that, look, I am describing a specific experiment, okay? So there are some experiments involving electrons that just treating electrons as particles is sufficient and will describe everything that you're going to measure. And there are experiments that you cannot explain if you just assume that electrons are standard particles. So you have to accept, swallow, and digest that there is not a simple explanation for what is the nature of matter. Matter is a particle / wave, okay? So you can call it whatever you want. You can give it a name that is it's of your own idea. So someone asked black matter. So I think you mentioned you want to mean dark matter. No, there is nothing about dark matter here. I'm talking about really electrons that we can see, we can detect. Mahmoud asked, what is black, but I mean, the actual meaning is dark matter. Well, we know that the universe, if we just assume that is composed, that we just compose I mean, if you assume that the universe is made of just the matter that we can see, we cannot explain the structure of the universe. So you have to, the universe must contain some sort of matter that we cannot see. And for this, we call dark matter. But I don't want to enter in details about that now. We can discuss that in a, sometime in an extra discussion session. Then Paul asked, why not call them wave particles? You can call that wave particles. You can call it. I mean, you can call wave particles particle waves. You can call paves. I mean, whatever you want. It's just that you don't have to stick to, you cannot stick to one type of description. You have to understand that there is a dual behavior in the game. Okay? Now, coming back to the slides. So we are just discussing that the electrons cannot be described as particles or waves all the time. Okay? And we have to find a dual description for them. But still, we can look at the results of this experiment of the double slit for 2 electrons. Sorry, for 2 electrons. The double slit for electrons, and understand the following. Since the electrons display an interference pattern as waves, we can associate to the electron a wave function, as we did when we discussed waves in the past, in the first double slit experiment. And I will call this wave function by this Greek letter called psi. Okay? So psi of x is a wave function that is associated to the electron. When just one slit is opened, I will call the wave function associated to that as psi j, and j can be 1 or 2, depending on which slit is opened. Okay? And now I can compute the intensity of, or I mean, more correctly, the probability distribution of finding electrons when just one slit is opened. And this will be absolute value of psi 1 or absolute value of psi 2 squared. This is exactly what we did to compute the intensity for the waves. It's just the wave function squared. But now, if I want to compute the intensity, or rather probability of the electrons on the second screen, I have to use the interference mathematics. So I have to use the fact that first I add the wave functions of the electrons, and then I take the square. Okay? So this psi is a wave associated to the electron, but you can ask, wave of what? Okay? Well, for the moment, this is just a mathematical way of describing what I see in the experiment. So I don't have a physical interpretation in the sense of something that you're going to see, something that you're going to take when you see the experiment, but I'm just associating to the electron a wave function. And the probability distribution that I see of finding the electrons is just the absolute value squared of the sum of these wave functions. Okay? This sum of the wave functions is the interference that is essentially the superposition of two waves. So we really need, in order to describe what we see for the electrons, we need to introduce a new concept, which is the concept of wave function for the electron. Okay? And this is exactly what de Broglie proposed just by thinking about symmetries. Okay? So all this is very complicated. I'm not saying that you should understand all the details just right away, but I'm just saying to you that seeing the double-slit experiment, you get a very strong suggestion that in order to describe electrons, you have to associate to them an object that has the properties of a wave function. Okay? Okay. There is a question in the chat. Can we still say that the wave function psi represents the amplitude in the case of electrons, just like in waves? That's a fantastic question. Yes, the wave function psi represents an amplitude, but then comes the question, amplitude of what? Okay, so this is what we're going to discuss now. So your question was just very nicely fit with the lecture. Okay. The probabilistic interpretation. The wave function, which is associated with this matter wave or the wave of matter of the electron, is going to be named from now on as the Schrödinger wave function. This is a very complicated name. I'm not even pronouncing it in the best way you could hear, but it's something like that. It's the Schrödinger wave function. And just by following this discussion we just had about on how we introduce the wave function, psi has the interpretation of a probability amplitude. See, this is very abstract. I'm saying to you that if you take, Felix is saying that this is the pronunciation. Thank you. Okay. I'm saying that if you take the wave function, you compute the square of the wave function, and you multiply by dx. Dx is just the region where we are looking at the probability of finding the electron. This will give to you the probability of finding the electron. So the wave function, as just raised, has an amplitude. Okay, so it's a wave, and therefore it has an amplitude. And if you compute the associated intensity of this wave, namely if you square the wave function, what you are going to get is a probability amplitude. Okay, so the wave function is a mathematical device in order to give you the probability of finding the electron or any other particle in some region of space. Okay, this is very abstract, and it takes time to understand what is going on. This interpretation that the wave function is associated with probability distribution is due to Max Born, okay? And this was done in 1928. So you see that we started the discussion about the quantization of radiation with Planck in 1900, and it's 1928, and people are just at this moment starting to understand what quantum mechanics is about, okay? So the fact that these probability amplitudes can interfere, and that, you know, these probability distributions are actually behaves as waves, is extremely non-trivial. And if we just think that the electron, I mean, we can still go back to our knowledge that the electron is a particle, behaves as a particle in most of the time. And we can think, well, the wave pattern that we see in the double-slit experiment is because the wave is a delocalized object that goes through, you saw that in the video. So the wave goes through both slits simultaneously, and when they pass through the slits, they interfere with each other, okay? But remember, I told you that when you throw electrons against the double slit, the detector clicks. So it behaves in a certain sense as a particle would behave, right? So in the example of the cannonball, either the cannonball will will arrive on the screen or it will not, okay? So we can try to fool the experiment. Let's try to fool the experiment. How do you do that? Well, I will try to send the electron against the double slit, and I'll try to detect at which slit the electron has passed through. So if I know that the electron has passed through slit 1, okay, and I would try to discover what happens with the electron in order to produce this pattern, okay? So we can really repeat the double slit experiment with electrons, but now we can turn on a flashlight against the slits. So this flashlight will emit light, and light will hit the electron. And when light hits the electron, it will be scattered by the electron, as we know, right, by the Compton effect. And I can detect here this scattered light ray, and I can tell you if the scattered light ray came from the slit 1 or from the slit 2. Okay, so this is a way of detecting from which slit the electron has passed. And in order to avoid any confusion, I will reduce the rate of electron emission by the source in such a way that just one electron will pass through the double slit. I mean, just one electron will pass per time unit. So I can really say that if I detect a scattered light ray, I will tell you from which slit it came from, and this is due to an electron. Okay, so I perform the experiment now, and I can tell you, well, electron came from slit 1, this electron came from slit 2, and this electron came from slit 2, and the other one from slit 1. And so I start really detecting all the electrons, and I can tell you which slit was the one crossed by the electron. Now comes the bizarre result. So you are here concentrated in seeing from which slit the electron passed by. And after a long period of time, you want to see what is the pattern that was constructed here, right? So you see that if you just perform the experiment and you don't see from which slit the electron came from, you're seeing a wave interference pattern on this screen. But now you're looking at which slit the electron is passing through. And when you turn your eye to the screen, you get a surprise. The interference the pattern that you see on the screen is not the pattern of a wave, but a pattern of particle. Okay, so when you turn, I mean, you don't see the interference pattern that you would see for a wave, but you see just the pattern that you see for a set of particles. So when you detect from which slit the electrons are passing through, you kill completely the interference pattern, and you see now a particle pattern. This is totally bizarre, right? So I'm just saying that if you don't know which was the slit that the electron crossed, you see a wave interference pattern on this screen. But now if you decide to know which was the slit that the electron passed through, you don't see the wave interference anymore, and you just see a particle pattern on the screen. So it's like nature is exactly, Paul, exactly. So nature is fooling us. If we don't know from which slit the electron came from, they appear to interfere as a wave. But if we detect from which slit the electron came from, then the electron just behaves as a boring particle and does not interfere as a wave. So nature conspires to not let you understand what is going on. Well, I'm being, this is just a joke, okay? But you see that what is important from this discussion here is that the act of measuring, okay, so this is a measurement. I'm just measuring what is the slit that the electron chooses. And when I do that, I change completely the outcome of the experiment, okay? So you can say, well, how can it be that the results are different? Well, the results are different because you're doing different things. In the first one, you don't interact with the system because you don't measure anything. You just wait until the end of the day and see what is registered on the screen. But if you decide to measure, when you measure, you are disturbing the system. The system is a different one from the previous system. Okay? And you can say, well, but in classical physics, so you see that if you measure the slit from which the electron came from, you recover the standard sum of probabilities. Okay. Well, you can say in classical physics, if I want to measure the position of a particle, namely, I want to measure the position of a soccer ball, I will have to interact with the system in some way, right? Because I cannot just decide where the ball is if I don't interact with the system. But then you are going to make you're going to perturb the system, but this perturbation can be small enough in such a way that the action of measuring where the ball is will not disturb too much the position of the ball. Okay? But how can you do that with an electron? An electron is a tiny, tiny particle with a very tiny mass. When you send light to interact with the electron, you are colliding an electron with a photon, right? And you are giving energy to this electron. And although it's a tiny fraction of energy for our macroscopic scales, this is a considerable amount of energy for the electrons. So you disturb the system in a very strong way. So measurements in the quantum world, they really change the system, because you cannot make the measurements arbitrarily small. Sorry, you cannot make the perturbations of the experiment arbitrarily small, because every measurement comes with some interaction with the system, and this can change completely the system. Okay, so this is a very, very important concept, that when you try to make measurements in the quantum world, you are going to affect the system in such a way that the outcome is different from the outcome that you were going to obtain if you did not disturb the system. And this is, I mean, you can think of this, the analog of that in the classical world. For instance, I want to measure what is the position of a ball. Okay, so I have a cannon with me that shoots cannonballs in a fixed direction, and let's assume that I kick a soccer ball that is flying, and I will measure the position of the soccer ball by shooting a cannonball against it. Okay, so I know that the position will be this one if the cannonball, if the soccer ball is hit by the cannonball. But of course, if I collide the soccer ball with the cannonball, then I will change the trajectory of the soccer ball after the collision. And therefore, the soccer ball will not follow the original trajectory that it was supposed to follow. Okay? So this is what happens in quantum mechanics, but in a much more severe way. And I'm also oversimplifying things here. But what I'm trying to say is that making measurements necessarily disturb the system in a considerable scale. So you cannot make the measurement and pretend that you're going to obtain the same result as before. That's the main point. Okay. Okay, so this closes the discussion about the double-slit experiment, which is a very rich source for understanding the very weird concepts of quantum theory. So what we're going to do from tomorrow on is to study a particular quantum system, which is the system will be made of light and polarizers. And we are going to try to describe the polarization of light in terms of photons. And for that, we will have to introduce all the formalism of quantum mechanics. So from tomorrow on, we are going to get our hands on really the modern theory and also the mathematics behind it. Okay? So I see that there are something in the chat. Yeah, so I think it was already answered. So I don't see any further question. The quiz will be based on the first week lecture or yeah, so I mean, the idea of the quiz is that you answer questions about everything that we discussed so far. So it can be about week 1, it can be about what I'm talking about in week 2. So, I mean, and the questions are questions that are meant to test if you understand the basics of what I'm saying. So I'm not going to give you, complicated questions or questions that will require a very deep thinking. It's just to test if the very basic things that I'm saying are familiar to you or not. Okay, so you don't have to worry about. I mean, you know, I will not make any trap so that you will not know how to answer. So people are asking, when is the quiz? I'm not sure if I want to tell you. I would prefer to give you an spontaneous quiz. Okay. But as I said, no, people are. So you want to have a date? Okay. So I I think that I can tell you. I mean, let's have a quiz on Friday. Okay, it's not a problem to tell you. But as I said, is it's really not. You don't have to expect of something complicated. It's really to test if you understood the basic elements of the basic things that I said. Okay. Okay. With that, I will close this session. I'm very excited for tomorrow and when we are going to start the formalism of quantum mechanics. Okay. So have a nice day. Take care and well, study. And I see you tomorrow. Bye bye.